Today we move into section 4.4, and the title is called Permutations with Repeated Elements. And I think you guys are going to really like today. It's a pretty sweet day, and lots of people are uncomfortable with the formal factorial notation when you have n's and n minus 1s. This should be a really nice day for you guys. It's a very clear day, and as long as you kind of are able to count a certain number of letters and use the factorial in your calculator, it's great. Now, before we begin, I just want to remind you guys a permutation. What's really, really important is that you recognize that order is important. And what you're trying to do is take a look at how many different ways can a number of elements or objects or things or numbers be arranged. And here's how we're going to do today. We're actually just going to start off with words. It's a great way to understand it. And then when you guys do the textbook assignment, you see there's other options, but they're all the same as what I'm going to show you guys. Now, the opening one, I need you guys to kind of come along with me with this analogy. What I want you to imagine is on your fridge, you have a bunch of magnets, and they're letters of the alphabet, all different letters, and you can have multiple F's and R's and I's. So I know this is getting a little messy, but what I want you to do is just imagine that you took all of the letters in the word Friday, and they were all on individual fridge magnets, and what you were going to do is you decided you were going to rearrange them. Okay? Maybe your little sister had put down Friday, and just to bother her, because that's sometimes what an older sibling does, is they rearrange the letters. If I said to you, well, how many different ways could you rearrange these 6 letters? It's actually a very, very easy solution. I'm just going to go equals. Yes, you could write down the word solution if you want to be fancy. It'd actually just be 6 factorial. And 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. Well, you wouldn't do that. You'd type it into your calculator. There would be 720 different ways you could arrange those to bother your little sister. It could look like this. You could take the Y in front. You could take the R in the back. And you wouldn't try to map that out in a tree diagram. What you would do is you'd just trust in the factorial. Now, I hope this isn't too quick, but now let's say we did the same thing. Let's say that each of the letters in Canada were on fridge magnets. And even though we're proud Canadians, we wanted to rearrange these letters, and then we wanted to say, well, how many different ways could we rearrange them? Now, for this guy, here is what the solution starts with, but then there's something extra that probably most of you, before I even show it to you guys, are anticipating. The solution would start with 6 factorial because there's 6. Now, I want you guys to watch. I'm just going to very quickly cover the camera up. And if you guys take a look at what is underneath, I took these letters and I took all the A's first and then the C, the N, and the D. Now, there's no debates on the C, the N, and the D. But imagine I rearrange these this first A. Well, is it this A, or this A? The second A, is it this one, or this one? And you guys get the idea. Now, what we don't do is get into a little internal battle and throw up our arms going, well, I don't know. This is the way that you could calculate it. Because you don't know which A is which, what we have to do is take that off. So it reduces really what is going on because they're exactly the same. They're triplets. What we do is we divide. There is 3 A's, so we simply divide by the number of repeated elements. And if you type this directly into your calculator, 6 factorial divided by 3 factorial, it really reduces how many different options you would have. When all the different letters are there, they're all different, well, we would have quite a few more arrangements. But because of the A's, and we just don't know which is which, and we don't fight that, there's going to be fewer number of options. Now, one of my favorites ever to show this idea would be then Mississippi. When you take a look at this, and if we count, we go across the top, there are 11 letters. So if these were all again on fridge magnets, imagine we were going to rearrange them, you would start off with 11 factorial. But then, here's the problem. There's a number of repeated things. If I start to count, 1, 2, 3, 4, there are 4 I's. But there's also 1, 2, 3, 4 S's, and there's also 2 P's. This is how we would get our final answer. Okay? And you would type it in, you'd go 11 factorial. I would still recommend putting this bottom in brackets to get the 34,650. That would be how we would get it. And then if you take a look at the bottom of the PDF notes, I wrote down a formal way to write it, and then you start to see it. Yep, there could be 1 thing repeated, there could be 2 things, there could be 3, there could be more repeats. the formula then makes a lot of sense. Now, what would be then maybe the highest level that you could do, and I won't rewrite it. What if I said to you, how many different ways could we rewrite Mississippi, but the M must be first? It changes the game just slightly. If the M must be first when we do this calculation, it's almost like the M is out of the picture. You only have 10 letters that you get to play around with. Yes, you still have 4 I's, 4 S's, and 2 P's, but if the M is first, it's like out of the equation, there's only 10 more letters that we get to move around.